So today in class, I'd like you to look at the section in your notes that talks about solving exponential and logarithmic functions. We're going to skip the exploration, and so really I'd like you to come down here and start where you were solving exponential equations. And this should kind of go along with what we've talked about for you to kind of start completing your zombie activity as well. So exponential equations are equations in which variable expressions occur as exponents. In other words, the x is going to be in the exponent. Okay? And there's two ways that you can really look at this. There's two types of problems. One, if it's possible to have both sides of your equation have the same base value, like b to the x and b to the y, then you know that your exponents are going to be the same as well, and you can really just focus on the exponent part of the problem. But again, this can only be used when each side of the equation has the same base or can be rewritten to have the same base. For example, if you look down here, I've got 2 to the x plus 1 power equals 4 to the x. Right now, the bases are not the same. But if there's a way I can rewrite one or both of them so that they are the same, I can use this property. For example, I'm going to leave this side as it is. However, I could rewrite 4 as 2 squared. I'm not changing the problem. 2 squared is the same as 4. But now I have this. And once your bases are the same, if the base values are the same, then your exponents should be the same or equal to each other as well. You can just solve the exponent part of this problem. But again, you can only do that when your base values are the same. And then from here, you would just be solving for x. I would subtract x and end up with x equals 1, and you're finished. Sometimes you have to change both the bases to something so that they match. For example, on example B, 9 to the 2x is equal to 27 to the x minus 1. Well, the common base that I see is both of these could be written with an exponent if I use a base of 3. So 9 could be written as 3 squared, and 27 could be written as 3 cubed. And again, I haven't changed any values. 3 squared is 9 and 3 cubed is 27. It's just writing it in a different way. But then what I end up with is when my bases are equal, then my exponents should be equal as well. So I end up with 2 times 2x equal to 3 times x minus 1. And there's an algebra problem I can just solve. This would be 4x. This is the distributive property, so I end up with 3x minus 3. When I subtract 3x to combine like terms, I end up with x equal to negative 3, and I am done. Sometimes, though, you're not going to be able to do that. If you look down here, for example, an example way down here, 4 to the x equals 11. Well, even I don't know just offhand how to write 11 as 4 to some power. You can tell it's not going to be a whole number. So sometimes this method doesn't work. So if that method doesn't work, you can solve by rewriting in log form, and you'll be able to solve for x. And this is kind of what we did in our zombie activity, to be able to solve for like the number of how many days would it take before the whole world was infected. This is kind of the method we used, okay? So I've established that the method above won't work for this because I don't know how to write 11 with a base of 4. However, if I can't solve it in exponential form, using my pattern from the previous part of this chapter, I can write this in log form. This problem would look like this. Log base 4 of 11 equals x. Well, from what we learned the other day, I can actually use the change of base formula and find this value. I would just need to type into the calculator log of 11 divided by log of 4, and that will give you my answer. So when I do that, 11 divided by log of 4, I get an answer of approximately 1.730. And you have just solved for x. Now, to be able to do this, though, you do need to remember that you do need to get the exponential part, the exponential part by itself first. So on this next example, the first thing I need to do is add 7 to both sides. And that would put me at 4 times e to the negative 0.3x power equals 20. I also need to get rid of the 4 because it should just be your base with your exponent left. So I would divide by 4. And so what I have is e to the negative 0.3x equals 5. Now please remember that when you go to convert this to log form, okay, this will look like this. It'll be log base e of 5 equals negative 0.3x. But please remember, log base e, that is the same thing as the natural log of 5 equals negative 0.3x. That you can find on the calculator. And so when you do the natural log of 5, you actually get a value of about 1.609. And that is equal to negative 0.3x. Well, you can see what to do from there to get x by itself. You would divide by negative 0.3. And you will get x equals 0.609 divided by negative 0.3. You get negative 5.363. And there is your solution. If we look at example C, this one's already in exponential form. It's b to the x equals y. When I convert this to log form, it will be log base 7 of 15 equals 9x. And just remember, when you're converting, the answer to the log problem should always be the exponent. So you always know the exponent's going to go on that side of the equation. This is something I can find on the calculator by doing log of 15 divided by log of 7. And that value is about 1.392. Since that's equal to 9x, to solve for x, I would need to divide that by 9. And my final answer comes out to be about 0.155. Another formula that you might look at and work with, and if you ever do need this formula, it would be provided for you, okay? It's called Newton's law of cooling, okay? This law states that for a cooling substance with initial temperature of T sub 0, the temperature T after T minutes can be modeled by this equation. Just ignore that rectangle, I don't know why it's there. Your temperature can be found by doing your original temperature minus T sub r, which is the surrounding temperature, okay, times e to the negative RT power plus T sub r. The little lowercase r is your cooling rate of the substance, okay? So if you look at this example, it says I'm making my famous chicken and noodle stew. When I take it off the stove, its temperature is 212 degrees Fahrenheit. The room temperature is 70 degrees, and the cooling rate is 0.046. How long will it take for the stew to serve to a serving temperature of 100 degrees? So the final temperature I want is 100. My initial temperature when I took it off the stove was 212. The room temperature, T sub r, is 70 degrees, okay, times e to the negative. Your cooling rate is 0.046. I don't know how long, so I'm going to leave that as a lowercase t, plus 70. Oops, I forgot my equal sign. There we go. And so now we need to figure out how can I get that lowercase t by itself. The first thing I would do is subtract 70. And we're just going to kind of work our way down. You can go ahead and do 212 minus 70 in the middle just to basically have less to deal with. That actually goes to 142 times e to the negative 0.046 t power. The next thing we'd want to do is divide by 142. And that will get you 0.211 equal to e to the negative 0.046 t power. This is an exponential form, and so from here, I'm going to come over here, we can change this to log form. It'll be log base e of 0.211 equals my exponent. And this is something that I can solve. Remember, this just means natural log. The natural log of 0.211 is about negative 1.556 equal to negative 0.046 t. And you can see from here, you would just divide by negative 0.046. And you will get 33.83. And it says that it doesn't really give your rate. So I think it's going to be in minutes. So about minutes. your time. You can now go back to Blackboard, and your assignment over solving exponential equations is located there.